Edexcel Decision 1, Graphs and Networks 3, Planarity and Floyd's Algorithms. Floyd's Algorithm, setting up initial tables. Floyd's algorithm finds the shortest path between every pair of vertices in a given network. You may remember that Dijkstra's does a similar thing of finding the shortest path, but Dijkstra's algorithm only finds the shortest path from one vertex to all the other vertices in a given network. Floyd's algorithm was first published in its current form in 1962 by Robert Floyd. Interestingly, at the same time, two other mathematicians, Roy and Warshall, also published the same algorithm. Therefore, you might find that the algorithm has other names, as you can see listed here. So Floyd's algorithm finds the shortest path between all the vertices in a given network, rather than just one, like Dijkstra's does. So in order to implement this algorithm, we first need to find a distance matrix and an initial root matrix for the network. Okay, so we'll first look at the distance matrix. So if we start with vertex A, we can see that if we're already at vertex A, we don't have to travel anywhere to get back to A. This is similar to all the leading diagonal. If we're at a vertex, we obviously don't need to travel to get to the same vertex. So then at A, we can see there's a direct link to vertex B of weight 9. There's a direct link to vertex C of weight 3. There's a direct link to vertex D of weight 5, but there's no direct link to E, so we use the infinity symbol. Similarly with B, we can see there's a direct link to A of weight 9. There's no direct link to C. There's no direct link to D. But there's a direct link to E of weight 4. So with vertex C, we can see that there's a direct link to A of weight 3. No direct link to B. There's a direct link to D of weight 3, and there's a direct link to E of weight 1. So now with vertex D, we can see this direct link of weight 5 to vertex A. There's no direct link to B. There's a direct link to C of weight 3, and a direct link to E of weight 6. And lastly, at vertex E, there's no direct link to A. There's a direct link to B of weight 4. A direct link to C of weight 1, and a direct link to D of weight 6. And if you look at the distance matrix, we can see that it's actually symmetrical about the leading diagonal. And this will always be the case because the graph is not directed. So that is one way of checking whether you're correct or not. Okay, so now we're ready to fill in our initial root matrix. So an initial root matrix tells us which vertex we get to first when we're travelling from one vertex to another. So in this case, obviously to travel from A to A, well, we're already there, so A is the first one we reach. Now we need to assume that every single vertex is directly linked with every other vertex to set up this root matrix. So if everything's linked, the first vertex we'll always get to is the destination vertex, A in this case. And in this case it will be B. And then if C is our destination and everything's linked to it, then we'll obviously get straight there. Same with D. And E. So as we implement Floyd's algorithm, we will be modifying this root matrix. So this is our distance matrix for the given network, and this is our initial root matrix. The initial root matrix will always look like this because we will always assume that there are direct links between every vertex. So now we're ready to implement Floyd's algorithm. So our next session will be Floyd's algorithm carrying out iterations.